Okay, 4-1 and 4-2. Real quick take, if I were to see something like this in the homework, f of x equals 4 over x, and we need to fill in, the table, we just do it the old-fashioned way, and every time we see a number, like -4 or -3 or whatever, we're just going to plug it into the function as we do. So, like, if we have f of x equals 4 over x, we're plugging in a -4, then that'll be something like f of x equals 4 over -4. Then you just figure out whatever that is. 4 over -4 is -1. Call it a day. Now, some of these are easier than others, and so if it gets a little bit intense, it's okay if you want to go calculator on it. We can do that at this point. Like if you had a 0.25, if you've got a good feel for how these things go, it's all right. But if you don't, it's okay too. And so like for this one, 0.25, you would have to go 4 over 0.25. And that 0.25 is negative this time, so that'll be a negative answer. But then you can either just figure out how many times that goes in, or else feel free to do it in a calculator and say 4 divided by 0.25 and call it good, What is that? I think it's like 16. I don't know. Tell me if I'm wrong, but I think it's like 16. And that's how these go. You're just filling in blanks on that one. Do your best on that. If I add something like number 2 here, we have the function x over x plus 1 minus 1. We got to figure out the following things, And so if I were to say, maybe take f of 11, that's us shoving in 11 every time I see an x. And so in this case, it would look something like 11 over 11 plus 1, and then minus 1. And then we're just figuring junk out. And so maybe I'd recommend it a piece at a time. If we were to start maybe down at here, I think I have a highlighter. Check that out. Highlight, whatever. If we were to start down there at the bottom, we could maybe just put the 11 plus 1 together. That's not a bad idea. So maybe we'll do that, call it a 12 or something. And so we have 11 on the top over 12 minus 1. And then it's just 11 out of 12 minus 1. And we got to make those bottoms match. It's time to do fractions now. 11 out of 12 minus 1 over 1. And then if we were to make the bottoms match there, you get times by 12 both times or something. And then we'll just see what that ends up looking like, because now the bottoms are both 12, and then we have 11 take away 12, because 1 times 12 is 12, So we have 11 take away 12. Let me undo those. And 11 take away 12 is, -1 or something. So it's -1 out of 12, and that's all you would need to put, -1 out of 12. It gets weirder as you start plugging fractions into other fractions. And so here's another one weird. Like if we had to do f of 1 over 11, that one's particularly weird because there we're plugging a fraction into an otherwise fraction-y problem already. And so that's a little bit intense. So let's look at that too. Here, maybe we'll erase our way to that. Okay. I'm hoping that this table's not making a huge amount of noise when we're recording. I don't know. We'll see. Let's try that now. I shouldn't have moved the answer. Oh well. If I were to try a 1 over 11 in there, this would be a 1/11th on the top where the x is. And then we'll put a 1/11th on the bottom again also. And so that's going to look like over 1/11th plus 1, and then we'll do minus 1, and then we'll just see how this all goes. And so from here, guys, 1/11th plus 1, I'm once again going to focus on the bottom here, and maybe we'll just leave the top be for a minute. So we'll just focus in on the bottom and see how that goes. And so let's see here. If we were to say 1 out of 11 on the top, that's the top thing still staying there, over, and then 1/11th plus 1, that's going to take a second because we got to get those bottoms to match. And so if we're to do that, this would be like an over 1, and then we got to get the bottoms to match, but the bottoms, it'd be like 11 or something. And so if I had that, let's see here, the bottoms are both 11, so it'll be something over 11, and then we'll go like 1 plus 1 times 11. So then, let's see here, 1 is easy, and then 1 times 11 is 11, so 1 plus 11 is like 12, I guess. So from there we'll say it looks like we got ourselves a 12, I guess. Ta-da, 12 over 11. Looking good. And then minus 1 we haven't dealt with, so we'll deal with that in a second. But right now I'd like to focus in on we still have this divide problem to deal with. And so remember, it is a divide. Whenever you see a fraction bar, that's not just 1/11th over 12/11ths. That's 1/11th divided by 12/11ths. And so that's a quick way to handle it. What we can do is we'll just say here, let's put a little diary border up there. And we'll say instead of taking this as just a fraction over another fraction, we'll write it as a divide problem. And we'll say this is 1/11th divided by 12/11ths. Looking good. And then all we got to do from there is remember how to divide fractions. And of course we have the minus 1 afterwards. But you might remember dividing fractions is like 1 over 11 times the upside down version times 11 out of 12. And then minus 1. We'll let the 11s cancel, and we got ourselves 1/12th, take away 1. And then we just kind of finish the game from there, because you got to like get the bottoms to match there once more time. This is me doing little ellipses, dots. You know, you'd go like 1 over 1, and then get the bottoms the same, and etc. That's kind of how those ones go. What else? Find the domain of a function. This is number 3. Find the domain of the function. Just remember, domain is the set of all the x's that can work without making this thing go nuts in a way that I can't handle it. And so maybe I could emphasize the bottom here. Hey, we'll emphasize the bottom here real quick to say that I just got to make sure that that bottom doesn't go to 0 in this case, because we're dealing with fraction-y stuff. So we're like, if 4x plus 9, if that becomes 0, we got problems. So I'm going to solve out for the x that makes that happen. 4x equals 0 minus negative 9. Divide into 4. We got x is negative 9/4. This is the suggestion here. We would say if we have that x is negative 9 out of 4, that is when it happens that my 4x plus 9 is 0. And if that happens, then this whole thing is undefined. So what we'll say is 4x minus 9, I don't want it to be 0. The one value, as they ask you, they say, what is the only value that's not in the domain? You would say, in this case, negative 9 out of 4 is the one thing that's not in the domain, because if I plug that in to my x over here, essentially the 4s are going to cancel, the 9s are going to cancel, we'll end up getting a 0 on the bottom, and this will be undefined. And I don't know how to deal with that. What else? Find all values of the variable for which the rational expression is undefined. Same kind of thing. We're just looking for what makes this thing undefined. It's just a little bit funkier here because the bottom is so much more intense, but it's not too bad. So I would take this one and maybe I'd just factor my way into it. And then once that thing is factored, we'll figure out what makes it equal to 0 and solve those both out, you know. So we got x's here, and then we'll be like, what goes into negative 9 adds up to 8. Probably some kind of like a 9 and a minus 1 thing, and then you just solve them both for 0 and call it a day. You know, we'll do the little like x minus 1, so it's like what minus 1 gives you a 0, and so it would be positive 1, and then here would be negative 9, you know. And so I'm looking at negative 9 or positive 1 in the version of the problem that I got anyway. Let's see. Okay, we got to find a y-intercept, x-intercept, and then vertical asymptotes. Okay. Probably the best approach here to look for those particular things is once again get this thing factored. So we'll just keep going until we got a bunch of factors going on with this stuff. Let's see here. It'd be handy to get the snowflake method going at this point, but whatever. Okay, on the top, we got 3x squared minus 2x minus 8. Maybe I'll send this over here. If I were to split that up, 3x squared, blank, blank, those are the new x's, minus 8. And I got to think of 3 times 8 is negative 24. What goes into that adds up to negative 2 from the middle here? And so, it's going to be like a 6 and 4 thing. That'll work. Okay, so let's do a minus 6x and a plus 4x, I guess. If we do that, it's getting a little bit messy down there. But if we do that, I think that this will work out well. because those do add up to the 2. Okay. Let's see here. If I were to see that from there, 3x minus 6x, or 3x squared minus 6x, they both have a 3x, and then that's x minus 2 left over, plus, and then if I were to look on this side, they both have 4 goes into both, and then I'd have an x minus 2 left with them. And then if we were looking for common factors on the right side and the left side, on the left and the right, we have both an x minus 2. They both have the x minus 2. And what's left is just the old 3x and the plus 4. So we got a factorization for the top, x minus 2, and 3x plus 4. Ooh, it's looking messy. I'm going to try and fix that. Here, let's figure that one out. 3x plus 4. Oh, yeah, way worse. Okay. And then let's try another color here. For the bottom one, same process. Let's see here, 3x squared, 10x 25, 3x squared, blank, blank, 25. X is minus 25. Okay, let's see how that goes. Now, 3 times negative 25 is negative 75. I got to figure out things that go into that. That'll add up to replace my negative 10. Shoot. 5 times 15. Yes, I think that'll work. Okay, so if I did minus 15x and plus 5x, that'll give us what we want. Looking good. And then we'll finish it like we did the last one. Splitting it up. Taking out a 3x, I'm getting an x minus 5. Plus, if I take out a 5 from both of these, I'm getting an x minus 5 left over. So we're looking at x minus 5 as the common factor, and 3x plus 5 is the leftovers. Looking good. Feel free to slow that down if you need help on your factoring or whatever. That's not something that comes real obvious to people, you know. Anyway, now that we got this factored, guys, here, I'm going to clean up some of this work so we can talk more details about asymptotes, but we'll keep the factors at the top. Now that we got that junk figured out, the intercepts and stuff will be easier to figure out by just staring at it. The intercepts and the asymptotes, etc. It'll be perfect. I'm doing my best to not leave any little blue marks around because I know how that bothers people. So I'm going to try and erase completely except for the factored, the factoring stuff here that we got. Okay, let's see how this goes. We got to find, I'm going to skip the y-intercept at this point. We'll come back for that. Let's look for the old x-intercepts and the vertical asymptotes. Now, x-intercepts, that's when the y value is 0, or in other words, if the function value ended up being 0. And so remember about that. If we're in factored form, it's enough to get the top of a fraction to be 0, and then we'll consider the whole thing to be equal to 0. Because if I ever had 0 over some number, like 0 over 1,000 or what, oh shoot, I just undid something. If I had 0 over 12 or something like that, I don't know, it would be enough to make the whole thing equal to 0. So if I'm looking to make x-intercepts happen, I need this whole thing to be 0. It'll be enough for us just to get the top to be 0. So we'll just focus in on these top guys and get them to be 0. And that'll be good for us. Okay, that being the case, we have 2 top guys. It's an x minus 2 and a 3x plus 4. Let's get those things to be 0. Okay, if x minus 2 is 0, then probably positive 2 is what it takes to get there, because 2, take away 2 makes 0, so positive 2 is one of them. But then a less obvious one would be when 3x plus 4 is 0, and you might have to solve that one out. After you do a few of them, you kind of see it, but you might have to algebra your way to it. If I want 3x plus 4 to be 0, we'll minus the 4. Then we'll have 3x equals negative 4, and we'll divide the 3. Pretend that says 3. Anyway, dividing the 3 on both sides, now I have negative 4 divided by what's supposed to be a 3. And so now we've got ourselves x-intercepts. We have a positive 2, and then the second one was negative 4 over 3. Those are some x-intercepts for us. Using the same kind of process, but now just dealing with the bottom, when we're looking for vertical asymptotes, we're just dealing with that. That's all we're doing, is we're going to say, well, what makes the bottom 0? Because then it'll be undefined, and when we go undefined, that's when we run into vertical asymptotes. And so, in this case, we have x minus 5 and 3x plus 5. By the same token, this positive 5 make it minus 5 makes 0. So we're going to say positive 5. But then on the other one, very similar process. If I were to take 3x plus 5 and equal it 0, minus the 5, divide the 3, you end up with a negative 5 over 3. Negative 5 over 3. I think I'm going to change colors because it's getting a little intense to look at. And then we will find, oh yeah, check this out, the old jet black. I guess it'll work along with the typing. Okay. Finally, a y-intercept is found when we just plug in. Remember, x-intercept, you zero out the y part. But for a y-intercept, you zero out the x part. You know what? I'm going to be dealing with, we'll have to choose a weird color. Hold on. Okay. Because I'm going to be pointing at some black ink stuff here. Check this out. Something I forgot. Oh, yeah. So when we're looking at a y-intercept, it's when the x's are 0. So we're going to put a 0 everywhere we see an x here. And you can do it in the factored version as well. I'm going to go ahead and do it in the original version. But whatever. And all we end up doing is, if we have 3 times 0 squared over here, I'm just putting zeros in the places because everywhere I see a 0, it's going to end up taking over. Like that last one, it was a 10x here. But 10 times 0, if I put a 0 where the x is, 10 times 0 is still 0. So they just zero out, and all you end up with is negative 8 over negative 25 left over because they don't got any x's. A negative into a negative will cancel, so you don't need the negatives. This is just 8 out of 25, and since that doesn't reduce, we found ourselves a y-intercept. That's about all I have for that one. Let's see here. Oh yeah, this is also interesting to mention. So, let's see. We have to find vertical asymptote here. Whoops. Oh, you know what? This is not all that intense. And so, for a vertical asymptote, just remember that's when it goes undefined. And so if we have 3x plus 6, I just got to figure out where does 3x plus 6 equal 0. And you can do that just straight away, or you could do it by factoring it and then figuring it out. It's whatever. But it's just like the last one. You're going to minus the 6. And then we'll divide the 3, and then you'll have yourselves something to work with. So if I divide the 3, we got negative 6 over 3, which is negative 2. It actually divides well, or else you can just leave it as a fraction if it doesn't divide well. Anyway, so we're looking at negative 2 for that one, and then you handle the other one similarly. No big deal. This is the one I was thinking about. Okay. Determine the long-run behavior. You got to kind of watch these ones, but I was going to give you guys a quick take on this, of course. So notice something about this. For the long-run behavior, remember, that means scratch out everything except for the leading terms. And so we're down to just x to the 2 over x to the 3 in this first case. And so what that means in the long run, though, is if we were to say x to the 2 over x to the 3, that means the bottom exponent is bigger than the top exponent. So the bottom is actually growing faster than the top is. And so if you're plugging in things like a billion, eventually you'll get to a place where you have some number on the top, but the bottom number is growing way, way, way faster than the top is. And if you ever see that, if you ever see that the power on the bottom is higher than the power on the top, that means that once again, the bottom number is growing way faster than the top is. And that means that we're getting tinier and tinier fractions, because as the denominator keeps on growing, that means I'm getting 5 out of 10, then 5 out of 100, 5 out of 1,000. I mean, I guess the top is growing too, but whatever. If the bottom is growing faster, we're essentially getting smaller and smaller fractions. So what we say in these situations, guys, is if ever you run into this, with a bottom number, the bottom exponent is bigger than the top one, you just say that the long-run behavior means we have, essentially, this thing is going to be bottoming out. It'll end up running into 0. And so you'll say something like this has a, what do we call that? A horizontal, I'm going to put HA, but it has a horizontal asymptote, not a vertical one, a horizontal asymptote, because it's essentially going to be running into, well, in particular, you'll see it running into the number 0. because this fraction, as you might notice, is approaching smaller and smaller and smaller and smaller. It's essentially approaching zero, even though it'll never quite hit it, just like when we're approaching infinity and we never quite hit that. And so we'll say it has a horizontal asymptote pretend that says at 0, or at y equals 0 in particular. I guess we could say that y equals 0, since I get to write all over the place on this thing. That's what I see. So whenever you see the power at the bottom higher than the power at the top, it represents this kind of a situation, and that means you're going to eventually be zeroing out the fraction. And so we just say it has a horizontal asymptote at y equals 0. It's kind of our quick graphing way to say that. Now, if we have, let's see, if we have the x2 and the x2, you see those powers are both matching, and so these things will be roughly the same no matter what. No matter what you plug in for x squared over x squared is roughly going to be the same. So the way we describe that, guys, is this thing at the long run behavior. The long run behavior, I pause and I think about it. It'll essentially be running into another horizontal asymptote, but not at 0 in this case. It'll be running into it at a particular value, and that's going to be dependent on what you see going on with these x squareds. Now, neither one of those has a number with it, which doesn't make for a very interesting situation. I guess I'll go ahead and just say it this way. If there's no number, there's always a 1, right? There's always a 1 next to your x squareds, and so in this case, if we plugged in 1 billion into both of those, they'd be growing at the same rate, so it essentially makes the x squareds irrelevant to each other because they're growing at the same rate. What we just got left is the number that was next to each of them, a 1 and a 1. So what this is approaching in the long run is it's approaching the number 1 over 1, or just 1. And it's still a horizontal asymptote. It's something that's like you have the graph going up or down for a while, and then it eventually just evens out. And in this case, it's not at the 0 line, it's at the 1 line, or 1 over 1 line. So it'd be like one step up, and eventually we're just evening out right at there. That's what's going on with this. If we had different numbers over here, besides 1x squared and 1x squared, then it would be evening out those numbers. I think we'll talk about that in the next problem. And then another situation is if you see the number on the top, the exponent on top is greater than the exponent on the bottom. What that means for us is essentially this graph is not going to even out like the other ones did. We won't have some horizontal asymptote. It won't be at 0. It won't be at 1. What it means, guys, is that just the opposite of the situation we had before is that the top is growing faster than the bottom. And so what this means is as you plug in bigger and bigger values for x, we're going to get huge numbers growing on the top over smaller numbers on the bottom. And so all that means for us graphically speaking is as I plug in bigger and bigger numbers for x farther and farther to the right, that my function value, my output value, is also growing huge because the top, the numerator, is so much bigger than the denominator. And so that means the y value is actually going to also grow up higher. And so as we grow, our x values keep going up to the right, so does our y value keep on going up and up. And so it just ends up being this kind of a slant asymptote, as we call it. And so, or we might also say it diverges or something like that. Anyway, and I guess that's what we'd be looking at here, guys, is if you have a power on the top is higher than the power on the bottom, then we say I get a slant asymptote out of that. And because it's all slanty, it keeps going up at the same time as it's going over. Anyway, something like that. We're to find a horizontal asymptote here. This one is interesting, kind of like the last one. Notice here on the numerator, the highest power is at degree 3, and then the highest power here is also degree 3. And so that means, even though they're mixed up, that means that it's just like the situation we had on the last one that I scribbled all over, where the x squareds matched, if you will. And so when the x squareds matched, we decided we handled the asymptote as just being the coefficients of 1 over 1, and then same situation here. It's just this time the coefficients don't match. This one has a coefficient of 3, and this one has a coefficient of -1. So our asymptote will be approaching the value of negative 3 as I plug in huger and huger values for x. Everything else will be canceling out because they're all smaller junk to deal with, so none of that will matter. And all we'll end up be dealing with is essentially just when I plug in billions of numbers into 3x to the 3. Whoa. Let's try that again. 3x to the 3 over negative 1x to the 3. And the x to the 3's will always be the same size. So the only thing you got left to compare the numerator and denominator is just the 3 over 1. And so that's kind of how we handle those. Okay, what else? Let's see here. Y-intercept, x-intercept, asymptotes, boom, boom, boom. Since this is a quick take, I won't go into it all. We've talked about y-intercepts and x-intercepts, and then vertical asymptote. Remember, that's where this thing goes undefined. So you got to factor that out and make it, figure out what makes the bottom equal 0. So that's what will make a vertical asymptote. And then if you wanted to find a horizontal asymptote, that's the thing we were just talking about, where we look at, the leading terms have the same power. It's an x squared and another x squared. So we're just going to look at the coefficients, and so it looks like a 3 over 2 would be, just pretend like you can read that. It's a 3 over 2 would be something that we're looking at for the horizontal asymptote, somewhere around there. Okay, find the equation of the slant asymptote here. So remember about this is we're just going to handle this by rewriting this in a friendlier way, because it's really hard to tell what the slant asymptote's going on when you have this much stuff. It's a little bit rough. Like we were saying before, the power on the top is higher than the power on the bottom, so it'll have a slant asymptote. But to know exactly what that is, remember that means that's the line that we're approaching. So if I have this slanty line, or the slanty asymptote going on where my graph is approaching something, we're suggesting that there is a straight line, like an mx plus b line, that we're approaching with that, with the function in a long-run behavior. After it's done with all its wiggling, it's going to eventually be approximating that line, approaching it anyway. And so that's hard to tell by just looking at these things. You can't just look at the coefficients. What we do is we'll rewrite the function, because remember, these are rational functions, and if you ever have something over something else, like we do here, we have a big polynomial over another little one. If we ever have that, the over bar, this bar that's like one over the other, their little fraction bar, is the same thing as a divide. But I'm not going to write it as a divide in the old-fashioned way. We'll write this as a long division problem. But remember, if I have an x squared and then a regular 5, I skipped over the x guy. Normally we have an x squared, then an x, and then their other number. So then we'll pull this old trick where it'll be like, well, I have a 2x squared. I don't want to skip over the x, so I'm going to say I have 0 x's and then minus 5. It's not the only way to do it, but it works well. And then on the inside, we'll do, this stuff. And so here we go, 2x3 minus 6x squared plus 7x minus 14. And we're just doing long division. Let's see if I can do this fast enough without being boring. 2x squared times something equals 2x to the 3. I think we just times it by another x there. And so then if I were to times that out, x times 2x squared is 2x3. X times 0x is 0x squared. Squared. And then x times minus 5 is minus 5x. Minusing that, now we have 2 take away 2 is gone. Negative 6 take away 0 is still negative 6 x squared. And then 7 take away a minus 5. So remember, that's take away of a minus, and so that's a double minus. So it's really a plus 5. So that's 7 plus 5 is 12x, and then we'll drop the 14. And then from there, let's see here, 2x squared going into 6x squared negative. The powers match, so 2 times, I guess we'll just do not plus, but like a minus 3. And I think that'll work. So let's try it. Negative 3 times by 2x squared will be negative 6x squared. It's good. And then negative 3 times 0x is 0x. And then negative 3 times negative 5 is positive 15. Looking good. We'll minus it. The 6's are out. And then 12 and 0 makes 12x. And then negative 14. And then we got to watch that minus again. It looks like a plus 15, but we're minusing it. So this is negative 14. Take away 15. And so that is negative 29. And what goes on with this, guys, now is essentially if I were to write this whole quotient out, we're saying x minus 3 is the main quotient part plus a remainder of 12x minus 29, because there's nothing left to drop. That's the remainder out of the original 2x squared plus, or whatever, minus 5 that we started with. And that's not all that important, except the analysis behind it. We're looking for a slant asymptote of what happens when I plug in a billion for x. And when we rewrite it this way, there's something clever about rewriting this stuff, because notice in the remainder that the power on the bottom is higher than the power on top, which means the bottom is growing faster than the top in the remainder part, not in the quotient part, but in the remainder part. And what that means is, as I plug in huger and huger numbers for x, what we'll witness is then, I can't remember what I was going to say. Well, yeah, what we'll witness is then these x's are getting huger and huger than these ones are. And eventually, it'll be like when we were talking about before, when the powers were higher on the bottom. And this thing will basically just be approaching 0. It'll just be wiping itself out. And all we'll be left with is just x minus 3 plus some chump change from over here. And so x minus 3, you'll notice, looks a little bit like an mx plus b type expression. And that's what we're essentially saying, is this part outside of the remainder that went away, that part is the equation of our line, our slant asymptote line. So we would say, well, at p, that line is just y equals x minus 3, or 1 over 1 x minus 3 if you wanted to make it look all mx plus b. But just x minus 3 is what we're looking for, or y equals x minus 3 would be fine, whatever. Anyway, that's what we're looking at with slant asymptote. You divide it, and then the quotient part stays as a line equation, and then the remainder just ends up going out to 0, basically. And then finally, let's see what else we got to say here. Oh yeah, so write an equation, it's got all these things. And so we're supposed to construct the equation. If I have vertical asymptotes, that's when we go undefined. So we're going to say, if I go undefined at x is negative 2, that means I have a factor of x plus 2, I guess. And if I have x equals 5, then x take away 5, well, it would be the factor I'd need to make it undefined at 5, because then I'd be like positive 5 minus 5 makes it 0. Okay, x-intercepts, same process, but remember those are the top parts, so I'd say like x minus 4 and x minus 6 would be the factors I'd need to make that happen. And the only other thing you got to watch out for then is they say it also has a y-intercept at 3. And that's interesting, because that means that if I were to have a y-intercept at 3, it means if I plug in 0 everywhere I see an x, then it's supposed to equal 3 as an output. And that's not necessarily going to happen. Let's see what happens if we did that. If we were to say right now, if we were to do a 0 in place of every one of those x's, that's 0 minus 4, and 0 minus 6, and 0 plus 2, and 0 minus 5. And we're wondering, it's supposed to question mark equal 3. It's supposed to, but I don't think that it will. And so we might have to adjust it. And so just like we've done in the past in similar situations, what we might have to do is, if this doesn't end up actually equaling 3, we'll have to times by, you can put it in the front if you like, but we'll times by some letter, we'll call it a, or some number, a multiplier, that will make it actually equal to 3, like we want it to be. So I'll keep that a around in case we need it. But let's see here, 0 minus 4 is negative 4, and then 0 minus 6 is negative 6, and then what else do we got? 2, and then negative 5. You can reduce those down or not, or whatever you want to do. Let's see here, that's 24 over 10. Or else if we reduce the 6 and the 2, that's 12 and 5, I guess. 12 over 5. which is interesting, but it's not 3. It's not equal to 3. And so what we'll have to do is we'll use our special multiplier. And so here's how the tricksters do it. You check this out. Okay, so what did we say that equaled to? This was 0. Okay, 4 and 6, that was 24 over 10 or 12 over 5 by the time we times it. And so let's see, it's 12 over 5 times some number that I got to use to fix this is supposed to equal 3. And then we just solve out for the a. But you might remember there's tricks about that. If I were to solve for the a, I can times by the reciprocal of 12 over 5 here. I'll just times the upside down version of that. And that should work, because times by a 5 over a 12, the 5s will cancel and the 12s will cancel, and I'll just be left with the a. That'll tell me what number to use for a. But just don't forget what you do to one side, you do to the other. So I'm going to times this by 5 out of 12, and that'll tell us what number a ends up being. And so then we can finally fix our function here. Let's see here. If I were to times that, the 3 and the 12 will cancel down to like a 1 and a 4, and so we have ourselves, if I were to times that across, that's a 5 times 1 is 5, 4 times 1 is 4. Looks like we got a 5 over 4, I guess. So a equals 5 over 4. And so finally what we get to say is the original function that we started out with, where we were just kind of taking notes on what they said, and they said, well, let's go ahead and make the vertical whatever and the intercepts and all this, and we came up with x minus 4 and x minus 6 and all that. It's fine. We just also have to times that all by whatever we found out our a number is, and so that's times by 5 over 4. So now we have 5/4 times with this whole big old fraction that we had from before. That's going to be our new function, f of x equals that, I guess. 5/4 times x minus 4, x minus 6, over x plus 2, x minus 5, giddy up.